Okay, we'll get started. And today we are talking about Bootstrap. Oh, it's week 9 Wednesday. It's the wrong day. Okay, Wednesday. All right. So on Monday we talked about randomization tests. Randomization tests. We built sampling distributions by re-randomizing our sample of data, or the random assignments, the treatments for the data. Today we're going to do something different, but it all centers around the idea of creating a sampling distribution. And so, I know we went over this on Monday and probably last Friday, but it bears repeating because if you're not good about sampling distributions, we're in trouble. Okay, so the sampling distribution of a statistic is the distribution of all possible values of a sample statistic from all possible random samples drawn from the population. All right, and by studying the sampling distribution, we can get a sense of how much a sample statistic can vary. And then if you have actual data, we can compare that observed statistic from your observed sample with the sampling distribution that we might generate if the null hypothesis were true. And then from there, you can calculate your p-values and things like that. So everything's based around a sampling distribution. Now, in your intro stats class, you covered the central limit theorem, and the central limit theorem forms kind of the foundation for all the inference that you do in intro stats, okay? And the central limit theorem says that the sampling distribution of the sample mean is going to be normal. Okay, we'll follow the normal distribution as long as these conditions are met, right? As long as the sample is drawn randomly, as long as your sample size is large enough. But it's going to say something along the lines that x bar is normal with a mean mu, population mean mu, and standard deviation equal to sigma, the population standard deviation sigma, divided by the square root of n. Okay, sampling distributions exist for any statistic that can be calculated from a sample. So anything that you can calculate from a sample, there's going to be a sampling distribution for it, okay? So, for example, you might have a sample of data and you fit a linear model and you get the slope coefficient. There's a sampling distribution for that slope coefficient B1, okay? So if you, because the idea there is that if somebody else drew a random sample from the population, they would fit a linear regression line, and their linear regression line might look slightly different, and they would have a different B1. Someone else draws a different sample from the population, they fit a linear model, they get a different slope, their B1 is a little different, right? And so everybody can draw different samples and get slightly different B1 values, and what's the distribution of the different slope coefficients, okay? That's going to be the sampling distribution of the slope, okay? So anything that you can calculate, R squared, I don't know, whatever else, right? Min, max, mean, median, standard deviation. It's going to have a sampling distribution. Now, the sampling distribution of other statistics, for example, the standard deviation or the variance or whatever, those are not governed by the central limit theorem, okay? And so those will not necessarily follow a normal distribution. All right? Now, whenever we simulate these sampling distributions, okay, so one way we can do this is we can rely on our mathematical knowledge of probability distributions, right? So you've taken 100B, or you're taking it right now or something, and you've learned about all of these probability distributions, right? You learned about the normal, and then the t distribution, and the chi-squared distribution, and the beta distribution, and gamma, and I don't know, right? You learn these distributions, and there's like relationships between them, right? Okay, so we can rely on our mathematical knowledge of these probability distributions, okay? But even if we have trouble remembering these relationships between distributions, we can always use simulations to kind of get a sense of what the sampling distribution looks like, right? Now, anytime we do a simulation, everything requires that we make assumptions about the population, right? And so this is an unavoidable thing. This is not all of statistics, but a big part of statistics is that we have to make assumptions about the population, because the whole idea is that the population is this big entity, and we can't observe it directly. We don't know exactly what the population looks like, and so we are looking at a sample. Based on what we see in the sample, we make assumptions to kind of fill in the rest, all right? So this is a side note, this same thing. So I said this to the other class, but sometimes, you'll meet new people, and then part of the conversation, what do you do? And I tell them, oh, I teach statistics, okay? And I get a few different responses. Sometimes people go, ooh, I hated taking statistics in college or something. And that always hurts my feelings when they say that, right? Because I'm like, oh man, when I took statistics in college, I loved it and it changed my life, and now I teach statistics because I loved it so much. True story. So anyway, and then another thing, sometimes the response I will get is like, oh, statistics is interesting because you can use statistics to say whatever you want, right? And this is always deeply offensive to me as well, because I've always seen statistics as a tool to find truth, and not something that we can manipulate for our own purposes. But where that sentiment is coming from is the fact that two people can look at the same data, but because these people, two statisticians, are making slightly different assumptions about the population, it could lead them to different conclusions. So that is true. Depending on the assumptions you are willing to make about the population, the same set of data could lead to different conclusions, okay? And so that does happen. And so anytime you make an assumption, you should be aware of the assumption that you are making, and you should be able to at least justify or defend the assumptions that you're making. And so that's a key thing, right? And so when we do randomization tests, we're assuming that because random assignment was used, it's reasonable to believe that the random assignment treatment, or the assignment of treatments, is exchangeable with another random assignment of treatments, okay? When we do bootstrap, we are going to be making assumptions about the population, and I'll try to explain these out in a moment, right? And so things that you might make assumptions about the population are going to be things like you're making assumptions about the shape of the population, or the population's mean and standard deviation, or the values that appear in the population. These are all different things that you might assume about the population, right? And so make these explicit, and once you have established these assumptions, then you can generate your sampling distribution by repeatedly drawing samples. All right, and so if the assumption about the population you're willing to make are parametric assumptions, then we are doing something called parametric bootstrap, okay? Parametric bootstrap, all right. So these first two bullet points are completely unnecessary, but I thought they were fun, so I included them here, all right? So bootstrap comes from the phrase to pull yourself up by your bootstraps, right? And so, I don't know, origins of the phrase, there's disputed, but one story that I liked, so I just put it in here, is that there was a German folktale where the hero was walking along, got stuck in a swamp, okay? And to get himself out of the swamp, he grabbed his bootstraps and pulled himself out, right? So it's a silly thing, absurd, but who knows, okay? The idea of pulling yourself up by your bootstraps is kind of the idea that, like, you don't ask for outside help, and you figure things out on your own, right? So you're in trouble, and your parent says, oh, you got to just pull yourself up by your bootstraps. That means I'm not going to give you any money, all right? You got to figure this out on your own. But anyway, with parametric bootstraps, the idea here is that we have a sample of data, we want to do something about the sampling distribution, and I don't have the luxury of going and gathering more data. So what do I do, right? So one thing is we're going to just have to make assumptions about the population. With parametric bootstrap, we assume the population follows a certain parametric distribution, like the normal distribution or the chi-square distribution. We say the population follows some theoretic probability distribution. That's the parametric part, okay? A lot of times we'll use statistics from our sample to help us specify this distribution, but not always, okay? And then what we do is we simulate drawing many random samples from this assumed population. For each of these random samples we draw, we calculate some statistic and record it, and then we build up our sampling distribution like that, and then we can perform statistical inference. All right, so here is an example, right? So a lot of you guys had to take SAT exams, especially if you were in the United States, okay? And so the SAT, there's the verbal and then the math. Technically, the official name is evidence-based reading and writing. Don't call it SAT verbal, but everybody, I think everybody just calls it verbal, right? So anyway, it's supposed to be normally distributed with a mean of 500 and a standard deviation of 100. Now, technically, if you look at the distribution of SAT scores, it is not going to be normal with this, and that's because the test takers are not representative of the entire population. Okay, it's supposed to be normalized on the entire population. Mean 500, standard deviation 100, okay? Scores, however, have a maximum of 800 and a minimum of 200 and have increments of 10, okay? And let's say you take a random sample of 15 students, their scores, okay? And the question is, what is the sampling distribution of the sample variance S squared, right? So you take your random sample of 15, you calculate the variance S squared, right? Somebody else takes a random sample of 15, they calculate a variance S squared. Someone else takes a random sample of 15, calculate variance S squared. Okay. So pop quiz, no points, right? But just pretend, right? Okay. What's the probability distribution that we can use to model this sampling distribution of the sample variance? Do you guys remember this? Sampling distribution of the sample variance? I think this is covered in 100B. Yes or no? No? Maybe? Nobody knows. Okay, well, perfect example where there is a theoretic answer to this, but maybe you don't know it, right? And that happens a lot, right? You go, oh, I bet there's some theoretic answer. You can look this up, okay? But if you can't figure it out, we can just use parametric bootstrap, okay? We can use parametric bootstrap. And so what we're going to do is we're going to set this up, okay? So here's just one example of a sample from this thing, right? So I do set seed 1. I use our norm. I'm going to generate 15 values where the mean is 500, standard deviation is 100, okay? And then I'm going to round these off to the nearest 10. So I'm going to use round these sample values to the -1 space, okay? -1 will round it to the tens place. And then we do an if-else. If it's bigger than 800, then change it to 800. Otherwise, use the samples value. Or if the value is less than 200, change it to 200. So that makes the maximum 800 and the minimum 200, and we're not going to get anything by that. And so these are some of the values that we might see: 440, 520, 420, something like that. Okay, and then we can ask what's the variance of this sample, and I get 10,120.95. Okay. All right, and so let's build up the sampling distribution. All I do is I take this exact code and I wrap it inside a for loop. Okay, so I'm going to keep everything stored in sample variances. We're going to have 10,000 of these, 10 to the 4. And then I say for I and sequence along, for each of these things, take a random sample of 15, round it, make sure the max is 800, make sure the min is 200. Calculate the variance of the sample, and then store that in sample variance as I. Okay, so we do this 10,000 times, and as for the summary, and we get a mean close to 10,000, which makes sense because our population has a standard deviation of 100, so it would have a variance of 10,000. The median's a little bit lower, and here's our max, and here's our min. And this is what our distribution looks like, okay? Does this shape look like any distribution you know? Maybe? Okay, well, all right. Answer to the pop quiz. what probability distribution can be used to model the sample variance of a sample of random normal values? The answer is the chi-squared distribution, right? And so if we say x1, x2, xn are IID from a normal distribution with mean mu and variance sigma squared, and we say s squared is the sample variance, then the distribution of the sample variance after multiplied by a constant follows the chi-squared distribution with n minus 1 degrees of freedom, right? So here's our s squared. If you multiply it by this constant, n minus 1 over sigma squared, this value comes from a chi-squared distribution with n minus 1 degrees of freedom, okay? And so here, I've generated all of these sample variances back here. So I take my sample variances and I multiply it by n minus 1 over sigma squared, 15 minus 1 divided by 100 squared. And then if I plot the theoretic chi-squared distribution on top of that, we see there's very close match between the two, okay? Very, very close match between these. So that's a good sign, right? But anyway, the point is that, whoops, even though we didn't know, even if we couldn't remember this theoretic answer, we're able to generate the sampling distribution, okay? We're able to generate the sampling distribution. And because we have the sampling distribution, we can get p-values and stuff for different questions, right? So here's a problem that somebody might ask, right? Let's say you get a random sample, or not random, let's say you just have a sample of 15 SAT scores where the variance is 20,000, okay? 20,000. Is it reasonable to believe that this is a random sample drawn from the population where the mean is 500 and standard deviation is 100, right? So is that reasonable? Okay. Well, we can get an empirical p-value by comparing our sample variance of 20,000 to the different simulated sampling distribution of variances, right? So we've done this back on a few slides back, and we can say, okay, how many of our randomly generated sample variances are over 20,000? Okay, so this is going to produce a logical true-false vector, and then if I take the mean, it's going to give us the proportion, all right? And it says, okay, yeah, you did get a few values over 20,000. It happened, looks like, with probability 0.012. So out of 10,000, I guess this happened 120 times, okay? So about a 1.2% probability, 0.012. And so, so this says, according to our simulated sampling distribution, a population where the standard deviation is 100 technically could produce a random sample where the variance is 20,000 or more, but that's only going to happen with a probability of 0.012. Okay, and so this empirical p-value is going to be low enough for me to reject the null hypothesis and conclude that my sample of scores is not really a random sample drawn from a population where the standard deviation is 100. Okay, so maybe it's not a random sample, maybe it's coming from a different population, who knows? I'm thinking it's not a random sample from this specified population. So I'm able to get p-values, and these are just estimated empirical p-values based on my sampling distribution, but it seems to work, okay? Here's another example, okay? Let's, we're going to continue working with the SAT verbal scores. So let's pretend a classroom has 25 students, and maybe these students are a random sample, right? This is probably a bad assumption because, at least in America, classes are not random samples. Like, they group the smart kids together and the kids who don't perform as well together, so they segregate students based on perceived ability, okay? And so, but anyway, let's just pretend we got a random sample of 25 students. What's the sampling distribution of the highest score in the sample, right? So we have 25, and now we're just looking at the highest score, okay? And maybe, what's the probability that the highest score is 750 or higher? So 750 is a good score. So what's the probability that the highest score is 750 if you got a random sample of 25, right? So technically, there is a theoretic distribution called the Gumbel distribution, and you can use that to describe the distribution of an extreme value, like the maximum or the minimum, okay? But I wrote, I doubt that many people know how to use it, or I'm sorry, I doubt many people know this or are familiar enough to use it. And the truth is I've forgotten how to use this. I don't know exactly how to use the Gumbel distribution either, but it's a thing that exists, right? You can look up extreme value theorems, and there's all sorts of distributions that can be used to model the largest or most extreme value, smallest value in a sample, okay? So we're in a situation where we don't know the theoretic answer, but we can get around this by using parametric bootstrap, right? So all of these things, it's just like, well, I don't know the exact answer, but let's just use the computer's random abilities. Let's throw it at the problem and see if we can get an estimated answer, right? And this is what we'll do in 102C, okay? So if you're a stats major, you take 102A, 102B, 102C. 102C is the Monte Carlo class, and we do a lot of this kind of stuff where we just take the computer's random ability, throw it at a problem, help us get our answers, okay? So anyway, we're going to have to make assumptions about what the population looks like. We're going to use the computer's randomness to generate some stuff. We're going to get some kind of sampling distribution. Okay, so my code looks very similar. I take my random sample of 25 values from the normal distribution. I use rnorm25, and then I convert them into SAT scores by rounding them, changing the max and the min. And then I'm going to just take the maximum value of my sample and store that away in my highest score. Okay, so so here's my random sample. I take the maximum value, put it away in highest score. Okay, and so we're going to record, see what happens, right? And this is what the distribution looks like. Okay, so the distribution, most of the time in a classroom of 25 random students, usually the maximum is somewhere between 650 and 700, okay? And certainly most of the values are between 600 and 750, okay? And it looks like there's kind of an artificial, because the SAT doesn't go higher than 800, we would probably expect a tail to go this way, but this tail is truncated and all of these people end up at 800 because, you can't get an SAT score higher than 800. 800 is the max. Okay, so this is what our distribution looks like, and maybe this technically the Gumbel distribution would look different because it would actually have the tail going out. Okay, so this is what it looks like, right? And then here the question is, what's the probability that the highest score is 750 or higher? Well, I just say, well, how many of my highest scores are 750 or higher, and then what proportion? So this will turn it into trues and falses, and I say, what's the mean to get my proportion? And it looks like there's a probability of around 16%, 0.1639, okay? So there's around 0.16 probability, right? And then I can change the question. What if we had a sample of 50 students instead of 25? What's the probability that in a sample of 50 students, the highest score is 750 or higher? What do you guys think? Okay. Well, we're pretty sure the answer is going to go higher, right? There's going to be a higher probability than 16% because now I've got a bigger sample, so now I've got like more chances of getting something higher than 750, okay? And again, doing the math for this might be hard, but even if you don't know the math, I think the idea of generating a sampling distribution like this is fairly simple. It's basically take a random sample. This time my random sample has size 50. And then I take the maximum value and I store those away, all right? So conceptually, I think this is fairly easy, and the idea of generating a sampling distribution after making some parametric assumptions is not a crazy hard thing to do, okay? And so anyway, I just say, how many times did my high score, how many times is that greater than or equal to 750? And that comes out close to 30%, okay? 0.2965, right? And there's your approximate answer, okay? Is it exact? No, it's not exact, but it's going to be pretty close to the truth. Is that okay? So parametric bootstrap is great. Okay, let's talk about non-parametric bootstrap, okay? So again, we're always making assumptions. We're always got to make some kind of assumption, all right? And so here we've got non-parametric bootstrap. And so if somebody talks about just bootstrap, they're almost always referring to non-parametric bootstrap. So in bootstrap in general is non-parametric bootstrap, but I guess I'm making a distinction here, okay? So non-parametric bootstrap does not make any parametric assumptions about the distribution of the population, okay? We're making assumptions about the population, but we're not making parametric ones, okay? The assumption in non-parametric bootstrap, okay, and this is the big assumption, is that our sample has been drawn randomly from the population, and therefore it can be expected to be representative of the population, okay? Does that feel like a reasonable assumption? I say, here's a random sample drawn from the population. Is it reasonable to think that this sample is representative of the population? Okay? Because that's the assumption we're making. We're going to say, I drew a random sample from the population. Because I drew a random sample, it's got to be reasonable to believe that this random sample is representative of the population. Okay? And there's a lot of things that are implied by this, and I'm going to kind of make these explicit, and some of these things will feel a little uncomfortable, okay? But if this original statement feels okay, then you got to be okay with the other statements I'm going to make, right? So the first statement is, my sample is random, and so my random sample, it's reasonable to believe that it is representative of the population, okay? So then what I'm going to do is I'm going to say, well, I don't know the actual population, but here is my random sample, so I'm going to just basically copy and paste it a whole bunch of times, okay? I'm going to like clone it a whole bunch of times, and now I've got a whole bunch of people, and I'm going to call this my population, okay? So it's kind of like in Photoshop, you can take like a patch of grass, and you can like clone it or stamp it and like cover like people you don't want to see, okay? And if you do this, you can build like a giant field of grass, okay? And probably from a distance, it seems reasonable, right? Like this patch of grass maybe is representative of all grass, and so you can just kind of clone it, and you'll get something that looks like a field of grass. Now, if there's something weird in that patch of grass, like there's a little red ball in the middle of it, and you clone it, then your field is going to look weird, right? Because that odd thing is going to get cloned everywhere, right? But we're hoping that if it's a random sample, it's got to be representative of the population, so I'm going to clone it, and we're going to get something that looks like the population. Now, maybe there's some issues there, but that's what we're going to do, okay? So in the computer, though, we don't actually have to go through this process of duplicating the data, okay? What we can do is we can just take the sample we have and sample with replacement. And if you sample with replacement, it is mathematically equivalent to taking it and making infinite copies of your sample, okay? So sampling with replacement is mathematically equivalent of just taking your current sample and then just cloning it an infinite number of times to build up the grand population, okay? Okay, and then we're going to draw samples from this pseudo population, or just sample with replacement, to build our sampling distribution. All right, so so here's some just key distinctions between kind of our sampling methods that we've covered, right? So if you got random data via random sampling from the population, you can use non-parametric bootstrap, okay? If you have data that from random sampling from the population and you are willing to make parametric assumptions about the population, then you can use parametric bootstrap, okay? And if your data was obtained via an experiment where random assignment was used, then you can use a randomization test, right? And so these are kind of the case uses. And so if you have a random experiment with a random assignment, don't use bootstrap, okay? And if you have data where the data was obtained via random sample, don't use randomization test, okay? So make sure you keep these in order, okay? And in all of these cases, we're creating a sampling distribution. All right, so this is straight from the textbook, okay? So I've linked in your next homework assignment, which I'm writing up and I'll post soon, I've linked a textbook, okay? And this textbook is free. You've already paid for it. Your tuition goes to the library, and the library has paid these publishers for access to these textbooks. So all you have to do is you have to be on the UCLA network, so either VPN in if you're off campus or just get it while you're here, okay? And you can get these textbooks, okay? No need to search online for illegal copies or something. Okay, so the Center for Immigration Studies at the United States Census Bureau has reported that despite shifts in the ethnic makeup of the immigrant population, Latin America and Mexico specifically remains the country's greatest source of immigrants. Although the average immigrant is approximately 40 years old, large numbers are children who enroll in U.S. schools upon arrival. Their subsequent educational achievement affects not only their own economic prospects, but also those of their families, communities, and the nation as a whole. So these researchers, Stamps and Bowen, studied the educational achievement of Latino immigrants by examining a random sample of the 2000 decennial census data, a subset of which is provided in latinoed.csv, the CSV file. So it's from the 2000 census, which I guess is already 20 years old now. But anyway, we're going to take a look at this. And so one interesting research question that has emerged from the research is whether there is a link between where the immigrants originated and their subsequent educational achievement. So we're just looking for some kind of association, not looking for a cause and effect relationship or anything like that. Okay. Specifically, the question is if there is a difference in the educational achievement of immigrants from Mexico and that of immigrants from other Latin American countries. Okay, so we're going to take a look. All right. If you take a look at the CSV file, there's different columns. Okay. And the columns of interest to us will be the Achieve score, okay? And this is the measure of educational achievement level. And this is some number between 1 and 100, where higher values indicate higher levels of educational achievement. Unfortunately, they did not provide more detail than this. So I don't know if when we see somebody that has educational achievement 50, I don't know what that means, okay? So I don't know, like, if somebody graduates from high school, what score they would get, or if somebody went on and become a doctor, I don't know what score that would get. So we don't know what these numbers actually mean. It just says higher numbers mean greater achievement, okay? And then the other variable will be this MEX variable, which will be, did the individual immigrate from Mexico, yes or no, okay? And these are all from Latin American countries. Okay, so here's just kind of a preview of the data, the first 6 rows. So we're going to be looking at this column Achieve and this column Mexico to see if there's a relationship, okay? And so here, just in our exploratory analysis, I say, okay, give me a summary by grouped by this variable Mexico. And so these are the values for immigrants not from Mexico, other Latin American countries, and we have 34 of them. Their mean achievement rating or achievement score is 64.5. And for the immigrants from Mexico, there's 116 of them. Their mean achievement score is 58.6, okay? And the difference between 64.5 and 58.6 is 5.9. All right, and the question is this difference of 5.9, is this statistically significant? Could this just be a result of randomness? Okay, just a little bit more for the exploratory analysis. Here's just a box plot, okay? The mean is not plotted here, we just get the median, okay? But the question is this difference between basically the centers, is that significant, or could it just be from randomness, right? And here's kind of a density plot, all right? And we have one that's in red and one that's in blue, and you know, are those different? Are the centers different? It's hard to say, right? So the classical approach is to just do a t-test, right? The t-test, we would say the mu for achievement level for immigrants from Mexico minus the achievement level for immigrants from other countries. There's no difference between them. We have a difference of 0 versus that difference is not 0, okay? And if you do that, you get a p-value of 0.0459, okay? what assumptions are we making if we do a traditional t-test? Okay, traditional t-test relies on the central limit theorem. We're assuming that the sampling distribution of the mean is normal. Okay, and maybe that's a reasonable assumption. Okay, maybe not, right? I think it's reasonable. I think it's reasonable in this case. Okay, but the point is we're going to do non-parametric bootstrap, right? So non-parametric bootstrap, we're going to resample our original data with replacement, and the key is that we're assuming that our sample is always representative of, our sample is representative of the population, and therefore I can sample with replacement, and that's effectively making infinite copies of my sample and using that stand-in for the population. Okay. The null hypothesis states that these two means are equal. Okay, and if we assume the variances are equal and that the means are equal, we're effectively saying that the values for both groups are coming from the same population. Okay, that the values for the achievement scores for Mexican immigrants comes from the same population as the values for the achievement scores for immigrants from other Latin American countries. All right, and so this is our setup for the non-parametric bootstrap. Okay, if the null hypothesis were true, the achievement scores for Mexican immigrants come from the same population as the achievement scores for other Latin American immigrants. Okay. With parametric bootstrap, we assume our sample of 150 observed achievement scores is representative of the entire population. And so what we're going to do is we're going to draw two random samples by resampling those 150 values with replacement. We're going to draw one sample with 116 and another sample of size 34. Okay, and we're going to calculate the difference between these two group means. We're going to repeat this a whole bunch of times, and then we're going to estimate our p-value by looking at the sampling distribution. Does this feel okay? Does this make sense? All right. Okay, so this is the code. Just a few lines here, okay? I just set up a place to store my differences, okay? And then this is it. This is the bootstrap right here, okay? We're going to sample this column, the Latino dollar sign achieved. That's the value, that's the column of 150 values, okay? And we're going to sample that with replacement. And that's effectively saying we're going to clone these 150 values and stand that in as the population, right? So we're going to do that. We draw 116 of these things and we throw them in group A. We do this again. We get 34 of them and throw them in group B, okay? Because we did this random sampling, we know that if there's a difference between group A and group B, that difference is just purely from random chance. There's no other reason why there would be a difference between group A and group B. We're just resampling the same population and throwing some in group A and some in group B. So we know all of these differences are a result of just randomness. Okay, and so the question is how many of those random differences end up having a difference greater than our observed difference? Our observed difference back here was established to be around 5.9, 5.92. So how many of these things end up with an observed difference greater than 5.92? Well, I say, okay, let's take the absolute value of those differences. We've got 10,000 of them. How many of them are greater than our observed difference of 5.9? Okay, and I guess around 4% of them, okay, 0.0465. That's the proportion that we get. Okay, 465 out of 10,000, that's around 4.65. So that's our estimated p-value, okay? And so this says that even if we drew samples from the same population, sometimes we get a difference of 5.9 or more from random chance alone. So this happens a little bit less than 5% of the time. And so our conclusion, whether we reject the null or don't reject, will depend on our significance level, right? If we go back to the t-test, our p-value is 0.0459, okay? 0.0459, and we're getting 0.0465. So our empirical p-value aligns quite closely, okay? So that's a good sign for us, right? Also probably an indication that the t-test assumptions are probably okay, All right. Okay, we could take a parametric approach to the same thing. Okay, so in parametric, again, we're going to, the null hypothesis, we're going to assume that both values or both groups are coming from the same population. And I'm just going to kind of skip ahead here. All right, these are all things that we've seen. And the assumptions that we're going to make is that the population is normally distributed. Okay, and maybe that's a good assumption, maybe that's not a good assumption. Okay, and because we're saying that both groups are coming from the same population, what we're going to do is we are going to just use the overall mean of all 150 observations as this population and for the population mean, and the overall standard deviation of our 150 values as the standard deviation of the population, right? Because the null hypothesis says group A, or the scores for achievement scores for Mexican immigrants comes from the same population as the achievement scores for immigrants from other Latin American countries. And so so here, that's what we're simulating. We're going to use the parametric assumption. We're going to use R norm, and we're going to use the mean from all 150 scores and the standard deviation from all 150 scores. So we say R norm 116 with mean M and standard deviation S, R norm 34 with mean M, standard deviation S. Okay, so we throw these into group A, group B. We calculate the difference between the mean of group A and the mean of group B. This generates our sampling distribution. And then we say, okay, how many of these sampling distributions, or not sampling distribution, how many of these differences in our sampling distribution is greater than the observed difference that we have? And this happened 0.0466, okay? So that aligns very closely with what we did in our non-parametric bootstrap. Non-parametric bootstrap, we got 0.0465. Here we get 0.0466. The t-test was 0.0459. Okay, so we're getting very, very close alignment in all of these answers. Okay, and so the our conclusion in all of these things will depend on what our significance level is. If you're using 5%, you would say, okay, we'll reject the null. If your significance is something like 1% or 2%, you would not reject the null. And there you go. But all of these, we're able to answer our questions either using the central limit theorem with the t-test or making assumptions about the population regarding it being just our sample being representative of the population, or that the population has a normal distribution. Now, for this one, it's always a good idea to check your assumptions, okay? And so for the parametric bootstrap, the assumption we made was that the population is normal. Maybe that's a good assumption, maybe not, right? So we should check this. This is what the distribution of 150 scores look like. Does this look like it could have come from a normal population? I don't know. I would be a little uncomfortable saying that this came from a normal population, okay? And then if we plot a QQ plot, does that look like a straight line? I would also feel uncomfortable saying this looks like a straight line and it comes from a normal thing. And so maybe it's not a good assumption to say that this population is normal, okay? So that might not be a good assumption. But we might be covered because the sampling distribution of the mean, because of the central limit theorem, is going to be normal as long as n is big, and our n's are 34 and 116, and those are generally considered big enough for the central limit theorem to kick in. So maybe we're okay. But anytime you do parametric bootstrap or anytime you do something, you just have to ask, is it reasonable to make this assumption? Okay, and even the assumption where you say my sample is representative of the population, there's some risk there, right? If there's something strange in your sample of data, like you've got an outlier, you might be making a mistake by doing bootstrap, okay? Because you're effectively copying a funny looking patch of grass, where there's a red ball in the middle, and you're copying that, and that could be a mistake. So this is where it's important to always have a little bit of domain knowledge, okay? So you should know something about the subject where you're studying the data, okay? So, one time I worked with a student that was, looking at some kidney patient data, okay? Unfortunately, nobody knew anything about kidney patient data. So I don't know, we didn't know what was a big number or small number. I didn't know any of this stuff. So we were just working completely in the blind. And I think that's a bad situation to be in, okay? You want to have an expert somewhere that says, hey, this number is big. This can't be a real number, because in my 20 years of experience looking at data, I know this should not happen, right? So you need somebody should be an expert in that field, okay, a domain expert, so that when you're going to do stuff, you can check whether your assumptions are reasonable or not. Okay, we'll call that a day for today, and maybe I'll see you guys on Friday. Maybe not. We'll see what happens to the attendance during our last couple of weeks of class, but we'll see you guys then. All right, stay safe, wash your hands, stay healthy. Okay.